Okay, so next up we're moving on to an example. And this example is an application problem about brine. So I went ahead and wrote out the word problem before I started recording because it's quite long. If you're taking your own notes freehand, go ahead and hit pause and copy that down for yourself. It's already written in everyone's skeleton notes if you're using that. And I'm going to read through the problem and kind of fill in this diagram as we try to figure out what this problem is about. So we're supposed to let X be the amount of salt in a 300-gallon tank. So I'm going to call this my 300-gallon tank. And inside that tank is brine that's added at concentration 2 pounds per gallon at 3 gallons per minute. So real quick, I just want to make sure I know that this tank is 300 gallons of brine. And the concentration, or the amount of salt inside that brine, we're going to call X. That's salt. Oops, I have to put that back on top. And then coming into the tank at 2 pounds per gallon and 3 gallons per minute is brine that's added. And so you might remember going over units in some kind of science class, but those gallons kind of cancel out, and we've got basically 6 pounds per minute of salt is coming in. And then leaving the tank at 3 gallons per minute is whatever brine we have inside. So 3 gallons per minute, something leaves. And then we're going to have to sort of address the idea that we need to describe what exactly is leaving. But we'll do that when we start writing the equations down. So the change in the amount of salt in the tank over time is going to be the difference between whatever comes in versus whatever comes out. And so what's coming in is 2 pounds per gallon of brine at 3 gallons per minute. Or like we said before, 6 pounds per minute of salt come in. And then what's leaving is going to be 3 gallons of brine per minute, but the concentration of brine is going to be that there's X pounds of salt within 300 gallons of brine. And that's going to help us sort of balance all the units in our equation so that everything matches. And so once we have all that, we can turn this into an initial value problem where we've got a differential equation. We just wrote it down. It's going to be 6 minus x over 100. And then the initial condition was given to us in the problem. I just hadn't written it down yet. We're told that there are initially 50 pounds of salt in the tank. So at the start of the problem, when time is 0, we have 50 pounds of salt. And we want to know how much salt there is in the tank after a long time. Similar to when we did that cooling cake problem, we can find the solution and then take a limit. Or we can think about equilibria. So the differential equation, if we set it equal to 0, is 0 equals 6 over 100, which means x star equal to 600 pounds of salt is an equilibrium value. And we could actually verify on the phase portrait that this is a stable equilibrium. I'm just going to tell you that because this section isn't about doing that. We'll do it without limits. So since it's stable, x is going to go to 600 as t goes to infinity. We would have to show a bit more work if we wanted to answer the question that way, but we can actually answer this question without solving it. Since we want lots of practice with solving linear equations, though, we're going to go ahead and do that. So we already have the ODE in the standard form. Oh, sorry, we need the ODE in the standard form, where we get dx dt plus something times x equal to f. So for us, we're just moving that x over 100 over. So we've got 1 over 100 times x, and that 6 can stay where it is. In this case, we've got p is equal to 1 over 100, and f is equal to 6. And we know that we're going to have to calculate that integral of p dt. It's a little bit confusing, I know, because we've always written like y of x, so integral of p with respect to x. But in this case, the derivative has independent variable t, so that's the one we integrate with respect to in this case. So I'm not going to leave that written down, that t equals x, because that'll be super confusing if you look at it later, but I just want you to know, when we look at the steps from before, we're treating t like what we called x. So that's going to be the integral of 1 over 100 with respect to t, which is just t over 100. And so then our e to integral p dt is just e to t over 100. And when we multiply that on both sides, we get the equations. Hold on, I'll write it out the regular way first. E to integral t over 100, e to t over 100 times dx over dt plus 1 over 100x is equal to e t over 100 times 6, which takes us to e to t over 100 times x instead of y now, and then the right hand side is unchanged. That's just that chain rule product rule step. So we want to integrate both sides. The integral of d e to t over 100 times x it's like that. And again, if it helps you to write this like d over dt dt, that's totally fine. But when we evaluate this integral, either way we're going to get t over 100, e to power t over 100x is equal to, e stays the same, and then we divide by 1 over 100, so we're multiplying by 100. Plus some unknown constant. And that means we're just going to have solution e is equal to 6 plus c e to minus t over 100. Because when we divide that over, it's going to cancel with the first and then introduce a negative exponential on the constant. So we have a general solution here, and then to finish out the problem, we need to apply our initial value. So we had the initial condition that x of 0 was equal to 50. That means we're going to have 50 is equal to 6. Oops. Sorry, in that step where I wrote my answer, I wrote 6 instead of 600. That's my bad. Please go back and correct it if you did the same. But 50 is going to be equal to 600 plus c e to minus t over 100 for t equal to 0. But e to 0 is 1, so that's just 600 plus c. That means that c is equal to minus 5 just 50 minus 600. And the solution is x is equal to 600 minus 550 e to minus t over 100. Which is great, we got the solution. The actual question was, how much salt is left in the tank after a long time? So with this solution, we actually have to go ahead and take a limit. After a long time means we take t to infinity. We go ahead and look at e to minus t over 100. And e to minus t goes to 0 as, t goes to infinity. So this limit is just 600, which is exactly what we thought the answer would be when we were looking at equilibria. So that's how we would finish out the problem. And if you're still writing, go ahead and hit pause and make sure that you've got everything written down the way you want it in your notes. I do want to talk a little bit about like what all the parts in this answer are though, so I'm going to have to switch pages on you. But so I just want to note that we get this answer because e to minus t over 100 goes to 0 as t goes to infinity. So x goes to 600 minus 0. That term that's going to 0 is kind of cool. Minus 550 e to minus t over 100. What's happening is it's dropping out of the solution as t goes to infinity. And there's a special word for that type of term. It's called a transient term. And what that means is that it initially is important and drives behavior of your solution. So exponentials, like they're very big functions usually, so it's doing a lot. But then it becomes less important. As the solution goes to equilibrium. And we're going to see a lot of solutions that have transient terms that go to equilibrium throughout the class. If you can think of any kind of system that kind of like wobbles around and then settles into some sort of consistent behavior, that's an example of transient terms and equilibrium states. There's lots of physical examples of that kind of thing, so usually you all in a engineering class tend to have personal examples of that. So we're just going to have one more example in this section, but we're going to save that for the next video.